Welcome to this open discussion. First, let me make this short announcement. Two announcements. Okay. First, this evening we don't have any formal plans. For those of you who are interested, the Israel Museum is open until Tuesdays until 9 o'clock in the evening, and there is an exhibition. Very recommended now about the relationship between ancient Egypt, it's called the Pharaohs, ancient Egypt and the Canaanites, the people that lived here. And one important part of this exhibition is about the invention of the alphabet. The claim is that it was invented in this area in very special circumstances, and they show how it came about and how the alphabet that started in Egypt became what it is today. So this is recommended for you if you don't collapse after this session. This is one announcement. The second one is that this session is recorded, but will be only our faces will be towards the camera. But the audio recordings as well as your beautiful backs will be on this film. So it's just for your information. I will not talk much, just by way of formal opening. Let me read to you a short paragraph that I'll explain and then say just very, very few sentences. And the paragraph that I want to read is from a book by Sylvan Bromberger from 1992. The book is called On What We Know We Don't Know. So it's on ignorance, but it's the complementary of information. And here is what he writes. I'm a very ignorant person, and I've long assiduously deplored this fact. Ignorance is an invitation to scorn. It presumably deprives one of all sorts of joys. It can't be put to any useful ends. It can't be eaten. It can't be given away. And it is damn difficult to get rid of in any other way. Only those who are totally ignorant about ignorance can believe that ignorance is bliss. But ignorance can also define and determine the value of scientific contributions. Its study should therefore be one aspect of the study of how scientific contributions can be assessed, and it should thereby become part of the philosophy of science. This fact, if it is a fact, holds a heartening hope for someone like me. It means that a cause of shame and embarrassment may yet turn out to be a sort of professional expertise. When you have a lemon, make a lemonade. This is what I propose to do here, and I invite you to share the refreshment, sour though it may turn out to be. So we're trying to make lemonade out of this lemon of ignorance and information. I'll say a few words about the physics that we heard today, and Mark will continue with the biology of yesterday, with the hope that we combine in this discussion both fields. We heard so much that I won't even try to give an overview or nothing like that. But I'd like to focus attention on 2 points that are of interest to me, and you may, of course, have very different interests for this discussion. One is the claim that came up in various ways yesterday as well as today about whether information is semantic or probabilistic, statistical, formal, whatever way you prefer to define it. Whether information has contents. Can it be without content, as Shannon, perhaps as some people understand Shannon? It was connected to fitness in Mike's talk yesterday, to Ulrich's talk yesterday about the semantics of about semantics, and in statistical meanings, various of them today. And the question that interests me is whether it is indeed the case that information can be without contents. Is there such a thing as information without contents? Because to quantify information, we need some probability distribution. And the question is, where does this distribution come from? And I submit that it comes from our knowledge about the dynamics of the source, if it's a physical system that has various states with various relative frequencies. So we put in a lot before we pretend to have something which is completely formal and doesn't have any contents. So this is one point that came up today and in different ways yesterday. Another aspect that came up in today's talk is the question information about what, but from a different perspective. We asked about, for example, whether in quantum mechanics there is such a thing, a different subject matter of information, and Olympia said that the subject matter is the same. It's just that the issue of encoding, and Yemima mentioned this. It came up in Daniel's talk, in my talk about information about macrostates, and finally in Rowley's talk about the Bekenstein information. So the question in the context of physics is also information about what, and is it meaningful to talk about information as being a formal quantity that has no content, no reference in the world? Does it even make sense, given what we've heard, especially today, but also yesterday? And if it does have something, if all these instances of information have something in common, if they do, which is the quantity of information, the abstract quantity of information, then the question is, since today we are in physics, is this abstract quantity physical in the sense that does it point to some property that is common to all these instances and that we quantify in the term of information? But in that case, it's again not abstract, but has a reference in the world. So this, all this direction of the contents of information and its reference is a point that I'd like to draw your attention from my perspective, but of course you can bring up any other question or comments that you want, that you find important and interesting. So please, Mark.
So yeah, my job is basically to highlight some ideas that were discussed yesterday at the biology day, and some things that I think were interesting, and I think sometimes because people agree, sometimes because they disagree. So in any case, I think they are worth discussing. So I'm going to highlight just 4 or 5 ideas very briefly. So first of all, it seems that most people agreed that understood information as a reduction of uncertainty, and in particular, something that seemed to be interesting is that they seem to agree that it's a non-factive state. So there was some discussion. So Dan and Leer had some discussion concerning this issue. So we don't know whether Floridi actually agrees, but most people seem to agree that state can carry information even if it's not true, and nobody seemed to complain concerning that idea, and that seemed to be something that most people agree yesterday. So second aspect that I think was interesting and relevant was that most people seem to assume that there was some measure of information that was common between physics, biology, and computation in a broad sense. So Rosa complained a bit. She says, well, I'm just talking about biology. And Ulrich also it wasn't completely clear, but many people push her in the direction of saying, well, this notion of information must be common between computation and biology, and actually Chagrier and other people put some examples. Michael also clearly connected information in biology to information in physics and so on. So that seemed to be a question that was on the table, right? So whether there is a sense in which an informational measure is common between all these different areas. Some people also today talk about that. There's a third issue, which I think was interesting, which was that the fact there is an informational relation is not enough for it to make it exploratorily interesting. Now, for instance, Ulrich and Ross especially, they said that, well, not all informational relations are interesting, we need something more, maybe a receiver, we need maybe some kind of coordination problem, we need maybe some kind of functional organization, but the mere fact that there is information is not enough for it to be exploratorily useful, so we need something else than that. So I think that was a point that was interesting, and other uses of information, like Michael's talk and Jeroen's, it was not obvious that they also, included some other condition. So that was another point of I think, agreement and disagreement. So, so another issue was that that Jeroen especially and Michael, that seems that information is a fuel for evolution, a fuel for complexity. So there's a relationship between information and the evolution of living systems. Jeroen defended that an informational approach can be contrasted to a Darwinian approach, while Michael suggested that there's a relationship between fitness and information, so that fitness can be cashed out in informational terms in certain circumstances. But definitely, it seemed that there was a close connection between information and the evolution of living systems. And finally, I think there's something interesting, not because many people talk about that, but because it was absent. So if you go to a workshop on information in biology, you will expect most people to talk about DNA, right? Information that DNA contains. And some people mention it, but just very briefly. And actually, they seem to disagree. So Michael at some point said that DNA carries information. And Rosa, I think at some point, seemed to be saying that according to her use, it's not obvious that DNA carries information in any interesting sense. So they seem to be mentioning this debate, but I think nobody got into it. But that might be an occasion for actually discussing whether information can be used in that context. And just some ideas that came up yesterday, and that if you want to discuss them, that will be fine. And otherwise, you can discuss anything that you think might be interesting. So now I think it's time to open the discussion. So I'm gonna be chairing. So please, if you have any question, comment, or anything, just raise your hand. So please, Aaron.
Should I get mine?
Oh, you need a microphone.
I'll do that.
I think in your joint introduction to the session, the words like measure and quantification or quantity came up at least 30 times. And I think this is an indication of an obsession that is blinding people to things that are not quantitative but are structural. And the earlier discussion where topology came up, for instance, I think is an illustration of that. Learning about topological structures is not the same sort of thing as learning about numbers, although there may be relationships between them. And I believe that a great deal of biology is concerned with topological structures and their properties, and a great deal of cognition is discovery of information about topological structures. For instance, nest-building birds, especially weaver birds, have to make knots. And if you can see a video of a young male weaver bird trying to make knots and not doing it very well, but gradually getting better. Well, you don't see it in the video, but you see the end result. Anyway, my point is that I think that this emphasis on quantity is a kind of blinkered mathematical view of the world, which leaves out a great deal of mathematics, which Euclid and Archimedes and other people before and after them paid a lot of attention to, and many current mathematicians do. And I think if you look at what young children are doing, a lot of what they're learning about the world is topological structures and relations and possibilities and impossibilities. Those are mathematical discoveries. So I'd just like to broaden things away from quantity and statistics and regularities, but also go to structures and possibilities and impossibilities.
So Neil?
I could go on a great piece, but you probably don't have
Thanks. I don't know if I can answer that, but I actually have my own questions. And I can probably hijack this discussion by just going through the questions one by one, but I'll just focus on two. One that pertains to what you discussed today, Orly, and also Rolly later on, about the role of information in physics. So you said something about the take-home message after a long and interesting discussion that in some sense information doesn't have an explanatory role if we adopt a view similar to yours in that sense. And so I'm wondering whether we can take from that the fact that maybe information is not as foundational as matter and energy according to some people like Wheeler, Stonier, Bekenstein perhaps, etc. And the other question pertains to something that you mentioned before, both of you, about Michael yesterday connecting function in the biological world and in the non-biological, still physical world. And I think, and I probably can't put it very coherently, but he suggested something about function in non-biological systems by appeal to either stability or stable states or structure or something of the sort. But then, and putting matters of time scale and the fact that we need to worry about closed systems versus open systems aside, I just think that there might be some tension with the fact that the second law of thermodynamics would actually suggest that we go into and constantly increasing entropy, and I think that suggests less order, less structure, and just more entropy in general.
I have a comment about the relation between semantic information and non-semantic or statistical information, something that Shannon already said we need to keep distinct, and Olympia today started out with the distinction and said those are two different things, and then you brought it up now. So, and I have actually written a little bit about this, and I'd be interested to hear any comments, if anybody has any, on what I see as an important connection between the two, where specifically mutual information and semantic information. So mutual information is a relation between a source and a receiver taken as a whole over all their possible states. So it doesn't tell you what any individual message means because it's just a measure of the relationship between the two systems. But if there is mutual information between a source and a receiver, for any given message that's received, at least insofar as there's no noise or equivocation, right? The correct message that's received, it tells us something about the source. It tells us what the state of the source was, and so it makes sense for me to say that we do gain some semantic information about the source anytime we receive a message from the source. So it's, in that sense, there is this connection. Of course, we can also interpret these messages, and it could tell us something else about other things too. But at the very least, it seems to me, if there's mutual information, there's also, for any message, something that it tells us about the state of the source, and that's a kind of semantic information. And if you have anything to add to that or to disagree, I'd be interested in that.
Yeah, sure. I don't know if this is an answer. I don't know if this is an answer to what you said, but there is this curious paradox when you try to calculate mutual information. Usually you average it over all possible messages. And then if you take each particular message, you say, what is the difference in entropy before this message arrived and after? And that difference of entropy, of course, can be positive or negative, because it could be that, I hear a weather report that says tomorrow 50% rain, 50% sunshine, and that decreased my entropy. So made it less certain what will happen tomorrow. But there's also another formulation of mutual information, and that is sum over all messages of the Kullback-Leibler divergence between the probability before and the probability after, where you say the probability after is the thing that is more true, the probability before is the thing that's less true, and the Kullback-Leibler describes how much better off you are when you get, when you know the truth, the more truth than the less truth. The Kullback-Leibler then is always positive, so it's sum over positive things. And then the interpretation is that for each message, the Kullback-Leibler divergence tells you how much better off you are. So there, the mutual information is kind of a thing that is summed over messages. And for each message, it tells you how much better off you are for this particular message.
But no weight function for a specific word or importance of...
So each one is weighted by the probability that message was sent. So it's sum over... Yeah.
Any other comments on that?
Yeah, sure.
I partially agree with you in the fact that once you are in the communicational context, you have already some kind of content of information. But what I tried to say this morning is that we can see information theory from a very, very abstract and completely formal view, as, for instance, presented in Covers and Thomas, where they began with a variable, another variable, and correlations between the variables, and no mentions of sources and destinations or nothing at all, but only variables and correlations. Once you have that, and you can also make some links with algorithmic complexity, because, well, they also explain how Shannon information and Shannon entropy can be seen as a kind of average on the complexity, algorithmic complexity of the messages of the search. So there is a formalism there that can be, in a certain sense, unified. But the source is nothing. The source is a variable, aleatory variable, a random variable. Nothing at all. No reference at all. Then you can begin with the different applications. One may be more physical, one may be more in engineering, about communication. I mean, I agree with the comment this morning that since Shannon was working for a telephone enterprise, I mean, he presented the problem was an engineering problem, but now we can take some kind of perspective and considering the theory as mathematical. With this view, we can use it, we have a lot of flexibility to use even in traditionally semantic context. I mean, like Dretske, he says, well, my theory is a semantic theory of information, but the basic formalism is the Shannon formalism. So I think that it can be useful for given, and I insist, even in the physical realm, I mean, I'm not saying that information is something physical from where all the things are done, but perhaps it can give some common language to different theories that can give us certain unification or common language to compare different theories without very strong ontological commitments, but of course with a certain content, because we are already in physics in this case, or perhaps in cognitive sciences, or in other different, for instance, when we are testing, in the work of testing hypotheses. And this is a completely different domain, and the formalism is still useful, and it acquires a different semantics in different domains. So I partially agree with you that when we are in communications, certain content you are talking about the source and the destination, but the information theory may be much more abstract than that, may be absolutely mathematical.
I'm going to change the subject slightly and talk about, at least the way I see it, relationship between physics and biology. I think what physicists, or what physics has told us, is that the world is hierarchically ordered. Whether physics has cut it at some of its real joints, nonetheless, the fact is there are certain constants of nature which allow you to break up the world in different levels, and part of the problem is how do you relate the various levels to one another. Physics deals with simple things, objects which have no memory, they're dumb, okay? And which allows eventually to correlate mathematics to it. This is something that John Herschel already realized way back in the 1820s, 1830s. What makes it possible for having this intimate mathematical relationship, the logic of mathematics and its properties? It's a little bit too bad that we only talk about physics and biology. It would have been very useful to have chemistry here, to look at more complex things. Topology has entered physics with a vengeance when you don't look at perturbative expansions, but look at more complicated things. Chemistry has to identify more complicated objects. Macromolecular chemistry is the chemistry of how does one chemical macromolecule identify another molecule, store the information, can recognize it, etc., etc. How do you translate that kind of knowledge and attribute it to the molecule? I don't have to say that biology is a much more complicated thing, which everything having memory, changing, etc., etc. But what is also important is the level of description. I used to be a historian of biology and worried about Mr. Darwin. And when Oren Cohn talked about evolution, modern synthesis of the 1940s, Darwin was much clearer. I mean, Darwin, before he actually had to write his Origin of Species, was at work on a big species book in which he attempted to get something about the dynamics of evolution. And his principle at the time was what drives evolution is the maximalization of the amount of life on the surface of the Earth per square area. And from that, he would deduce natural selection, et cetera, by looking at smaller things. So within his scheme of looking at individuals, holobionts could easily be integrated into that. Okay, so you have an individual which has bacteria which you didn't know about, but a different form of individual, and it still maximizes the entire thing. So all I'm trying to say, I think we have to be very careful, or we should try to be careful about the level of description at each time. What is the mathematics which refers to it? How to use it? we use the same word for entropy, which really relates to very many different levels of description. And so my point is really to understand under what circumstances, what kind of mathematics are relevant, and how do we produce new mathematics, and that's what's happening at the present time in a very, very deep way.
Ronnie?
Well, I mean, I had a point that was following up on that earlier.
Okay.
I mean, so I could hold off or go back to it, but I mean, yeah, I agree there's an interesting set of questions here about, you know, what Shannon says and whether it should be taken at face value, and when you sort of unpack the theory, whether or not there are implicit semantic commitments. But in the case that was just given there, I think one thing to point out is you can have lots of information flow where the receiver is still, you know, paralyzed when it comes to behaving. A receiver can get lots of information in the Shannon sense, and it could be behaviorally irrelevant to it. So it could be left with uncertainty, which, you know, while its uncertainty has been reduced, it's no better off in terms of, you know, the decisions that it has to make for which act to perform. And if you think that, you know, for a sign to carry semantic information, it has to have the kind of function of carrying that information, and you think that there are these cases where you can have signs carrying information that sort of make the receiver in no better of a position to act, then it's clear that you can have cases where there's kind of mutual information, but the sign, it can't possibly have the function of carrying that information because it doesn't in any way help the organism. So I think that that's one of the kind of key things about, you know, the aboutness of information sort of ties really closely with how, you know, how does it improve the receiver's kind of prospects for acting as opposed to just kind of reduction in uncertainty. So I think that that's the kind of important case to consider when you know, think about that case.
Okay. More comments, suggestions?
I'm afraid I don't know your name, but thank you for your comments. I think there are aspects of biology which haven't come up yet, but are very relevant. For instance, we talk about the information that organisms have and which they use, and information in the genome and how that's encoded and how it's expressed and so on. There's something else that needs to be said, that as evolution and the physical world with volcanoes and all sorts of other things change, sets of opportunities and constraints change, which are not directly products of evolution, but they are crucial to the opportunities and constraints that biological systems are faced with. And they have structure. And in some sense, for example, there are organisms that just float around in liquid, and they do or do not get the chemicals they need in their immediate environment. And there may be some noxious chemicals and good ones, so they have to be able to make a distinction between which ones they let in and which they'll let out. They may have to have some control over the amount of liquid that flows in and out under osmotic pressure. If you let too much in, you explode, and so on. You let too much out, you collapse. But at other stages, organisms may be on a solid surface which has different features in different places with a kind of stability and a collection of topological and metrical relationships. And at any time, the individual can only have a small subset of the information that's required about that layout. So evolution had a challenge, and I'm saying this is a challenge that comes from the environment, which has an informational structure, and then somehow evolution has to produce organisms that can get that information, store it, and then use it when necessary. Like when you need liquids of some sort, you go there. When you need a particular kind of nutrient, you go there. And when you're going from there to there, beware of that bit where you previously got stuck, and so on. So that requires all sorts of different kinds of information, some of which come from the inherited information structure, but some of it comes from the environment, and the interplay between them is part of what we have to understand if we want to understand the role of information in biology. And I think a great deal of it will be geometrical and topological and not numerical.
Just I want to say something related to what Ron says and other people. So something that I think an interesting idea that came up yesterday was that it's not enough to have some kind of correlation in order for that information to be explanatory useful in any way. So in order to get something more robust, like maybe semantic information, we need to look at the receiver, we need to look at how the system uses this information or the functional role. But something interesting that came up yesterday, I think, is that Michael pointed out that functions can also be captured in informational terms maybe, so that there's a process of selection and then you get certain information between certain states. So it might be possible to actually capture the function of the receiver also in informational terms. So, you might get a way of capturing this additional feature that you need in order to get robust semantic information, maybe by appealing to the kind of reduction of uncertainty of the. Well, I don't know. I think that was an idea that was interesting, suggested yesterday. So maybe.
Well, it's good because it's a kind of additional comment from what you said. I mean, I think that up to this point, each one was talking about what each one knows, physicists from physics and biologists from biology. I will try to say something about what I see when I hear about information in biology. And my sense is that it's true that in biology, like in physics, information needs to have some content. So perhaps it must have some aboutness. I mean, it must be semantic in a certain sense. Okay, but this is not enough. I mean, this is not free us to try to develop a theory or something, let's say, theoretical, more strongly theoretical, like the presentation of Mark yesterday, and where things can be mathematized, even if not quantified, but something that can be described in a more theoretical way. Because if we only say that, well, the organism takes information from the environment and then acts according to that information, and then the meaning of that information influences the behavior. If I change in all the discourse information by knowledge, it's changing. So if information is something different than knowledge, it must be because there is some theoretical informational theory for biology. And when I say about biology, I'm saying about some domain of biology, because biology is very wide, and it's not the same biology of behavior biology or evolutionary biology or the DNA and molecular biology. For instance, in molecular biology, I've heard that some people had tried to use Shannon information, and they have problems because, in principle, all the sequences are equal probable. But we know that there are many, many sequences that have no biological interest. So they should not be counted there. So they say, well, see, since Shannon theory does not take into account the relevance, cannot be used. Perhaps this is something that I'm questioning myself. Perhaps somebody who works in biology can answer. Perhaps the idea of complexity, algorithmic complexity, I mean, information in the computational sense that can be applied to each individual sequence, and does not need to have a search with different capabilities, but that measures not uncertainty, it's not related with uncertainty, but with compression of messages, individual messages. Perhaps it's better to use in molecular biology. I mean, I'm waiting an effort from biology to try to find some theoretical tools to talk about information in a fruitful way. This is what I'm waiting. I'm trying to insist. Perhaps I say this may be a good idea or not. And no, I want to say that many times it's funny because many times I try to say perhaps this can be no. Biology is too complex. We cannot use those tools. I mean, well, but perhaps trying to make an effort, it's a good thing. This is my point.
Yeah,
So, yeah, I would like to raise maybe a skeptical point about the value of talking about information at all, which connects to Rosa's and also to Uri's talks yesterday, right? Because, I mean, the notion of information, at least that philosophers of biology, of cognitive science, and I saw also physics, work with is extremely liberal, right? There is information everywhere. And what Rosa and Uri were trying to do in their talks, at least, was to provide further constraints on which kinds of information can be useful in explanation, right? And those constraints need some kind of justification themselves, right? And which kind of justification are we going to provide? Are they going to be merely pragmatic in the sense that talk of information, so it's a talk, helps us to capture more easily some phenomena that we are interested in explaining, or does it add something? And you also mentioned this, right, briefly. Does it add anything that is not captured by explanation in other terms, in non-informational terms? It is perhaps a synthetic way of explaining things, but is it adding anything else in relation to other kinds of explanation, be them physical explanation or physiological explanation in the case of biology? So my fear is that, again, talk of information is very often, and especially, I guess, of semantic information, is very often metaphorical, and many times we fail to notice that we are using it metaphorically, and this brings a series of risks to our theorizing. Right? So I'd like to hear more about that. I mean,
well, I mean, I'll say one thing about the idea of using the language metaphorically. So one thing that didn't come up, but that's sort of important in the literature on biological information, is this idea that the function of informational descriptions is to kind of draw our attention as theorists to salient and important similarities between the biological system and some kind of paradigmatic computational system or information processing system, and in so doing kind of raise new questions, suggest new hypotheses. And so you might think, or you might not think, as you look back on the history of molecular biology, that that's exactly what happened when people were looking for the DNA code, or and people have debates about that. But there, it's not so much a question of like, does this sort of give us a superior explanation? It's more of a kind of, how does this facilitate the, discovery and concept formation and things of this sort. And I see that as an important alternative role for kind of this language to play. Now you might think, you know, insofar as biological systems are designed, adapted systems, that that kind of informational language is likely to play a more important role in that sense in biology than in physics. But maybe not. You know, you might think, well, you'd expect to find kind of something like the genetic code in an adapted system because it faces certain kinds of computational problems that need to be overcome. But when you're looking at systems that aren't the kind of cumulative product of a selective process, then, you know, why think that there should be some kind of deep similarity between artifacts which we have designed to, you know, solve certain problems and you know, the physical system in question, which is just sort of doing its thing and not, you know, the result of a kind of long selective process. So I think that, you know, if that's the role or one of the roles you think informational language plays, you might think it has a role to play in biology which it doesn't have to play in physics. Yeah.
Thanks. Yeah, perhaps just some comments about this eliminativism about information, possibly, or question about how valuable is it. So, as you mentioned, one of the thoughts one can have is, well, does it add anything extra? And I think I'm a bit suspicious about that as a requirement, because it seems a bit too demanding. So I'm in line with Ron's comment there that as long as it can be shown that by using informational language or terms or concepts, we can highlight certain features that perhaps we could talk about in other ways as well, but nonetheless that make certain features salient in explanations, then that has as such explanatory value for it, or it improves the quality of an information if that's the case. So what I have in mind here, for instance, is it's not about quite coding, but I've looked at, sorry, not about information, but I looked at Crick's use of coding and gammos in the 1950s. And when they talked about a code, so in one way they used it for the mapping sense of amino acids to template units, but there were other terms around, of course, and they used them like a scheme, for instance, right? It just or a correspondence. But my sense is that by using code, they were able to highlight a particular property of that relation, namely a property such that if you have, you know, a string of one sort of thing, and then you have a mapping to another alphabet, then you can generate one from the other, basically. And that was a way, or well, that's my view anyway. That was a way to highlight that particular property. But you could have used a scheme as well, you know, and just added that. So that's a claim about it's being perhaps too strong. The second comment on that is, if you're a naturalist about information or meaning, then you would expect that whatever meaning is, or representation is, or information is, you can, you know, spell it out in terms that do not appeal to anything like information or representation. So one would expect that there is a vocabulary available but by which you can refer to whatever the informational processes are. So again, you can then say, well, why should we use then informational language? Well, there's, you know, it becomes identical if you're a naturalist about that.
Just another point along the same line, but also answering the question in the beginning. And as an example of something which elucidates and doesn't purport to be a big descriptive add-on and still adds a lot to how you do science and what you can achieve, is the negative aspect of information. That is not what you say or what you can now say if it's a language, but what you don't say or what you prohibit yourself from saying. And what I mean is, in physics, we'd call it no-go theorems, especially in quantum information theory, right? No deleting, no communication, or how can I break this no-go theorem? And they're all very much informational. You can even look at, you know, the boundary of speed of light as speed of information as a no-go theorem if you're so inclined. And when I say that what you can't say delineates more than a positive language, there's some common sense to it, but then there's also a lot, at least as a physicist, constraints give you a lot more than just the furniture of your system. Because when you have constraints, you can say a lot about the shape of the functions there and how they interact, but it's not just on that level. If you look at biochemistry, if you look at things like that, there's work on information in biology that puts the finger specifically on information as added constraints on the foldability on the tertiary level of proteins. So adding just the right amount of constraints gives you a certain level of information. Adding too much constraints is actually bad. And so it's both on an abstract level of the language that you use, what you cannot say, and then therefore there's more meaning to the things that you do say, and also on the practical level. And I think this goes all the way back to the original meaning of information, both in Shannon and in what Orly described as information is physical. Landauer's information is physical as information erasure, meaning that if information pertains to physical reality on all its levels, I have a strong feeling that it's going to have to do with this negative aspect. Not as in negative with the connotation, the negative connotation, but in the sense of a directing, and if Olympia is manipulating, but not directly, but by giving it the spaces where it doesn't go, that kind of influence.
Okay, so Rosa had a question as well. Comment.
So a bunch of people have said, you know, information is really useful. It helps us generate new hypotheses and ideas, and it draws our attention to things that are important, and you know, it gives us new insight into the systems. I feel like saying that is pretty different from being a hardcore realist about information, right? It seems like when it's playing this kind of very instrumental role, that's saying something very different from, you know, it refers to something real in the world that we would be leaving out if we didn't use informational explanations there, right? You could make something salient just by making it, you know, writing it bigger in your pictures. You can think about things in new ways just by telling stories that you know are fictional. I think Arnon had a view something like this about information. So I think in order for us to be like really committed realists about information, you have to say more than just it helps us along and it guides our thinking in, you know, productive ways. You have to say something more specific about why this concept is latching on to some fact in the world.
Yeah, back. Yeah. No.